Hi everyone. In the times of managed services, you might ask, why even manage your own databases? There are so many companies eager to do that for you and to take all of that load away from you. Don't worry about your backups, don't worry about your high availability. They will run it for you. So why just run it yourself and go through all the pain of having to take care of everything? The reason might surprise you, and one of the reasons, at least for us, is the storage limits, because our databases, I can tell you, probably 70–80% of them would not fit in any of these offerings. You might argue, well, but you could move to Aurora or AlloyDB, they offer higher limits for storage, but I ask you, is Aurora and AlloyDB Postgres anymore, even? My name is Teresa Lopes and I'm a database engineer at Adyen. What I'm here to talk about today. First of all, let's define what's exactly a big database, and we will see that size is not all that matters. Next, I will share some strategies with you that we apply at Adyen to be able to manage these huge databases. Of course, this would not be a Postgres talk if a vacuum was not involved. Second to last, my favorite topic, backups. And finally, what we do with all of this data that we collect. Let's start with big, but how big? Before I start, just a reminder, we self-host our databases, so we manage the underlying infrastructure, and we run our databases on top of bare metal servers. So no Kubernetes just yet. Back to what is a big database. Maybe let's start defining what is actually a small database. So if you have a small database with very low TPS, it can look like something like this. A country road, very quiet, easy to manage. Next, you can have a very, very big database in terms of data, but very low TPS. And even though there are some challenges about storage, having low TPS, it kind of makes it easier to manage. Now is where all the fun starts. Having a small database should be easy to manage, but if you have high TPS, you start having concurrency problems, issues. There are still some tuning, some normal performance improvements that can be done to be able to manage these ones. But now I want to add a new dimension to this problem, that is strict latency. Adyen operates in the payments industry, financial industry, so strict latency is a requirement for us. And if you have a very small database but with very strict latency requirements, you can still manage them as long as you do some optimizations. So what exactly do we manage at Adyen? I like to call it perfect storm. And what do I mean by this? They are usually massive databases, so lots and lots of data. Very high TPS. Like I mentioned, strict latency requirements. And we have to keep lots of hot data around all the time. It kind of looks like this, a huge mess. So how do we manage this? First things first, let's start with the easy part, the easiest. And it's what I would call bring balance to the database. And what does this mean? Imagine you have a single instance. Why on earth does your single instance has to do with all the writes and all the reads by itself? Just divide to conquer. Have a primary for your writes and replicas as many as you need for reads. You can even set up cascade replication, where replicas replicate from replicas, avoiding having to attach too many replicas to the same primary which can overload the primary. But of course, there are no free lunches. Whenever setting up replication, you need to make a big decision, either sync or async. And trust me, both of them have trade-offs. It all depends what is important to you. And I have to be honest, we do manage both types of replication. Some systems, async is just fine. Some other simple systems have different requirements, and we do need to have sync replication. So again, you have to figure out what is more important to you. Losing a primary and not being able to write, but as long as your reads are always available, maybe that fulfills your business requirements. Maybe your writes can never be down, and maybe your replicas can be lagging behind. So you need to decide on any of these topics and then pick the most suitable replication profile for you. Lots could be said about sync and async replication, but I will leave you here two really great resources that will go in much deep on this topic. One of them is a talk Alexander Kukishkin gave at PGConf Germany last year. And another one is from a colleague of mine where he shares some interesting story on some strange behaviors we encountered while using sync replication. Next, vacuum. You know, people say there are two things certain in life: taxes and debt. If you manage Postgres databases, I will add a third one: vacuum. Yes, you cannot simply avoid vacuum. Well, unless you want your database to stop working, which I imagine is not the case. And why is vacuum so problematic? Or what makes vacuum so problematic, at least for us? For us, it's all about the wall generation, because we have all wall generation due to inserts, deletes, updates, and so on, transactional workloads. But then vacuum also generates walls. And like I mentioned before, we have lots of replicas. All of our clusters have replicas. And all of these changes, if they are coming from inserts or from vacuum, they need to be replicated and applied on the replicas. So for us, the most important thing is to keep the wall generation predictable and under control. And this also means keep vacuum under control. Okay, that's fine, but how bad can it be? It turns out it can be really, really bad. Imagine having a table of 10 terabytes plus a couple of indexes, try to vacuum, and then let me know how long it took. And by the way, don't have tables that are 10 terabytes in size, okay? It doesn't help with vacuum. So how do we keep this under control, and how do we manage vacuum? Once again, let's start with the basics. First of all, take a look at your vacuum defaults in your database, because I would say 99% of the times they are really not very good for the majority of the workloads. What do I mean by the normal auto-vacuum parameters? So auto-vacuum thresholds, vacuum scale factor, the analyze ones as well. The auto-vacuum max workers, if you have lots of resources on your server, why not just give it a bit more to vacuum? Of course, you also need to check the auto-vacuum work mem or maintenance work mem, depending how you configure it. And do not forget to enable logging, because you don't want to be going through your logs when you have a problem just to find that you didn't log any auto-vacuum or vacuum related activities. So enable logging from the start. As you can imagine, this kind of didn't solve our problems, even with those parameters very well tuned. We had to go a bit further. And I want to present you two concepts in vacuum, auto-vacuum. that interact with each other, and they are the cost and delay. In a very simplistic way, represents a wall cycle. On the vertical axis, you have the cost that vacuum is allowed to do before it has to take a break. And then on the horizontal axis, you have the delay, that is the break between vacuum cycles in a simplified manner. And what is the wall generation is essentially the area underneath these lines. In reality, these lines are more triangle shaped, but this is just for the sake of the example. So how these parameters interact with each other? Let's increase the cost for the same delay. And let's start with this wall cycle graph. Let's focus on a time window. And now let's allow vacuum to do more for each one of the runs before it has to sleep. So essentially we are increasing the cost, the vertical axis. And if we focus on the same time window, you can see that essentially you can generate way more wall for the same time period. And this can lead to bursts of wall if you have the cost parameters too high. So you allow vacuum to do lots of work and it will generate lots of wall during that time. On the good side is usually vacuum total times is shorter, usually. Now let's see how this changes if we actually increase the delays, so the time we allow vacuum to rest between cycles. So let's pick up where we left off. Same time window, and now we will just tell vacuum to have a bigger break between the cycles and how it will look like. For the same time window, you now see that less wall gets generated. You still have the spikes because we kept the cost constant, but they are more spread around in time. So you need to try to find the balance between these two parameters so you can keep your wall generation under control, keep your replication lags under control, and for that you need to keep your vacuum under control. As you can imagine, this was also not where we stopped. So we still rely on manual vacuums quite a bit. And how do we use manual vacuum? We schedule it, so we have certain triggering conditions that will schedule the manual vacuums. I will just quickly go over some. So we check the top plotted tables and then we schedule the vacuum to run in the order that we want, not the order that auto vacuum would decide to do, because we know our databases, we know how they are used, and we know which tables are more important to be vacuumed first. We do same logic applies for freezing tables. We also have some triggering conditions around wraparound vacuums. Top big tables, same logic, the order, because here is all about enforcing the order that we prefer. And finally, we also use this option, index cleanup off. And honestly, I will just quote Christoph Pettus because he said it better than I could ever say. So, unless you are sure you know what you are doing, that is, you are in a wraparound point emergency, please pretend this option does not exist. Really. And why is Christoph so pessimist, let's say, about this option? And to be fair, I think he's completely right. Because what happens is, when you use this option, you are telling Postgres to vacuum your tables, but to skip the indexes. So no work is done on the indexes. And you have to ask yourself, would you trust your indexes that were not vacuumed for months? Yes, that's the thing. Postgres might stop trusting them as well. So if you are in a situation where you do have to use this option, don't forget to re-index your indexes. Also, if you are running under Postgres 17, please do upgrade, because lots of great improvements were done in Postgres 17. Final words around manual vacuum is, if you run manual vacuums, which I hope you don't have to, but if you do, please do not forget to run analyze, because auto vacuum takes care of this for you, but vacuum does not. So you have to take care of it by yourself. Finally, my favorite topic, backups. How do we even backup these huge databases, 100 terabytes, 200 terabytes, 300 terabytes? How long does it take? So I can tell you that we do not use PG-based backup. Even though it has been greatly improved over the last years, incremental backups were added as a feature to it. It simply takes too much time. Our databases are very, very big, like I mentioned, but they are also very, very busy. So if you try to run a PG-based backup on a very, very big database, you will find yourself in a bad position. And I mentioned incremental backups. That could help us, but you still have to take a full backup now and then. You know why? Because your incremental backups might be corrupted. They might disappear. So you don't want to rely on 2 months of incremental backups. So you still have to take, initial first full backup, some incremental backups, wall backups, but then maybe every week, every 2 weeks, I don't know, it depends on your requirements, you should still go and get a new full backup. So before I tell you how we do it, I want to share a bit more about backups. And I want to share with you some very scientific math. What do I mean by this? For me, a backup is as good as a backup and restore. If you tell me that you have backups, I will ask you when was the last time you restored them. Because you don't want to find out that your backups are no good when you are in a crisis mode trying to restore them. And you also want to know how long it takes to restore them. And you want to get familiar with this process of backing up, restoring. None of this should be news to you whenever a disaster occurs. Because if you do not test your backup restore strategy frequently, you might have to end up reading this book, which might exist or not. So finally, I will share how do we do the backups of these huge databases. And it's fairly simple in theory. We rely on the storage snapshots, and then we back up the wall files so we can have point-in-time recovery. But I was just talking about restores. So how do we test the restores? Because a backup is nothing without the restore. We have lots of clones. So we provision daily clones of twice a day for some systems. We provision clones of our biggest systems, and we actually provide these clones to the developers for them to test new features, test the release, run analytics on them, and so on and so forth. So it's not just testing that the restore works, but it's actually testing that the data that was restored is the right data. Finally, data. We collect lots of them, as you can imagine. And you might ask, do you need to keep it all? Why? Why do you keep all of this data? Why do you collect all of this data? People sometimes ask me. I will tell you, we collect the data because we have to collect the data and keep the data, especially due to regulatory requirements. And we have to keep it for some time, but we can keep it in a more efficient way. And now I will show you what I mean by that. One of the strategies that we use to keep the storage footprint somehow under control is what I call get your columns in order. So let's start with a very simple basic example. One table, 4 columns, Boolean, int, small int, big int. That's it. Then I will insert a record into this table. True, 1, 2, 3. Again, simple table, simple record. I will now use an extension page inspect to show you how Postgres internally stores this record that we just inserted. And if you get the information with page inspect, you will get something like this. And I will just try to make a visual representation on how this is actually stored. So first we store the Boolean, then the int, the small int, and then the big int. And as you can see, you have some green part and we have like an empty part. It's what we call padding. There must be a better way of doing this. And yes, there is, and I will show you. So with the same record, the only change I did, so the record is exactly the same values, but what I did is I swapped the columns around. And how did I reorder the columns? I first stored the big int, then the int, small int, and finally the Boolean. Do you see the difference? I know I have heard it all. This is over-engineering. This is too much. This is too much. It's too complex. And I agree. I don't think you should start doing this if your database is 100 gigabytes or even 1 terabyte. But I will share some more very scientific mathematics with you. If 10% of 100 terabytes is 10 terabytes, so we are potentially looking at a savings of 10 terabytes. And I mentioned that we have replicas. All of our systems have replicas. So again, this small gain, it starts to compound. And you should have backups, and we do have backups. So these savings also translate into some savings in the backups, on the backups. And we don't run just a single cluster. We run hundreds of clusters with hundreds of replicas if you add up all of them. So this really, really compounds over time. There are lots of caveats around reorganizing your columns, but I want to again share 2 great resources with you for you to learn more about this. One of them is the PostFM podcast episode by Nikolai and Michael, Column Tetris, and another one is a great talk that Charlie Batista gave at FOSDEM a couple of years ago. There is a recording, go and check it out. One of the other things we do to be able to keep our storage footprint under control and also to keep wall generation under control and so on and so forth is partition. At Adyen, we rely on partition a lot. And what is this all about? The way I see it is you have a big problem, just break it into smaller problems. That's it. Sounds easy enough, right? And this works very well if your database has 1 table, which I assume it does not. So you might end up in a situation like this, where you have to join multiple tables. They are partitioned with different strategies. They are not really aligned, and this can become really messy. And what happens is you can end up in a situation like this, where the planning time of your queries is way higher than the execution time of your queries. And that doesn't sound really right? The Postgres should not spend 120 times more planning time than executing time. So be aware when you are dealing with highly partitioned environments, keep track of your planning times and the execution times, not just the total execution times. Next, do you remember when I asked, do you need to keep all of this data? Yes, we do, but do you need to keep it all together? Maybe not. So imagine we're processing a payment. Today, maybe tomorrow. This data is really, really hot. It's really important that we can retrieve it as fast as possible. You are making payments. This information needs to be written and read really, really fast. But after a week, maybe after a month, are you really looking back to this information or even changing it? Changing it, probably not much. Reading it, maybe more for some analytics and so on. But after 1 year, are you really, really changing or even reading this data? Most likely not, but we are still required to keep this data around for several years, depending on where in the world we are operating. So if you need to keep the data, keep it, but don't keep it all together. Just break it apart. Don't keep your cold data together with your very hot data, because this will just slow you down. So offload this cold data to a secondary database, to an S3 bucket somewhere. Because now, with this old and cold data, the requirement is durability, is no longer performance. Talking about performance, just sharing some final tips about what do we do to make our queries more performant. One of them is we heavily rely on prepared statements. But be careful with prepared statements. They are very, very useful if your data distribution is even. So if you are doing primary key lookups, it's easy. You can reuse the same plan all the time. You calculate the plan once and then you just reuse the plan all the time. So you don't have to do the planning phase for your statements. You just go directly into execution phase. But if your data distribution is skewed, you might be preparing a plan that works for a subset of your data, but then it works really bad for this other subset of the data. So be aware of your data distribution if you want to use prepared statements. Talking about plans. So you can still use prepared plans for even if your data is highly skewed, but you need to be aware of it. And what you can do is force generic plans for when you know your query is targeting data that is not skewed. And if you know that specific queries will target data that is more skewed, you can force custom plan, which means your Postgres will replan, calculate a new plan, and then execute that new plan for that specific query session only. These parameters can be changed at session level. So you can have a default for the entire database, but then for specific cases that you know that will not be suitable to be run under a generic plan, you can force a custom plan at session level. So let's just wrap up on what I've been sharing here today. We started by checking what is a big database, and we learned that it's not just about the size, it's about how busy it is, if you have strict latency requirements, if you need to keep lots of hot data around or not. Next, I shared with you a strategy that we use to bring balance to our databases. And don't forget, this is a trade-off, sync versus async replication. Next, lots of things were said about vacuum. Once again, the defaults are not really good. Do change them and don't forget the logging. My favorite topic, backups. I shared a little bit how we do our backups, and don't forget your restores, of course. And finally, I also shared some strategies that we use to reduce our storage footprint as much as possible without impacting the performance. Final words. There is no such thing as a solution fits all, and even inside of our fleet we have different solutions for different systems. In my opinion, when you manage mission critical systems, especially at this scale, the most important thing is actually having predictable systems. No one wants to wake up by a PagerDuty alert at 3 a.m. because a query suddenly flipped, the plan flipped, and now the performance is terrible. Another thing is you might not be able to control the amount of data that you need to keep or have. That's true. It does not depend. Usually does not depend on the database engineers. But there is something you can certainly do, that is you can control how you store it. So don't forget, don't keep it all together. Divide to conquer. So it's up to you to decide which battle you want to pick. Doing nothing and suffer, or just engineering your way out of it. One thing I'm sure, Postgres can deal with these huge databases and kind of crazy workloads, and my company is the living proof of that. I'm really curious to know if you run similar workloads on Kubernetes, because I would love to see it. So thank you so much, and see you next time. Bye-bye.